This talk is on combining Rust and Python together with the library Pyo3. And this talk will focus on calling Rust from Python. So why even do this? Well, the reason why is that we want to take advantage of Python's flexibility and rapid development cycle with Rust's performance and, most important, safety. Rust guarantees that you will not have memory leaks. Rust also has guarantees of no data races when running parallel threads, which is really important because data races can be difficult to debug. They may not show up in your test code, and they may only intermittently show up in production. So to enable this in an easy manner, people developed Pyo3, and this library, it's short for Pythonium trioxide, which is like an ode to Rust's chemical formula. But a fun fact, Rust isn't named after the rusting metal. It's actually named after the fungus rust, which attacks crops. So now, who uses this Pyo3 library? Why do we care? Well, there's quite a few other projects that use Pyo3, everything ranging from web servers to JSON parsers to the AI community, and then also the science community with stochastic processes, being able to perform those in Python using Rust. And also WebAssembly uses Pyo3. And why do they use this? Well, besides the safety, there's speed. And so if we look at one of the examples in the Pyo3 library, and we're going to explore this more in the demo, that for this word counting example on a 4-core VM, I saw a 17x speed up. This is being compared against straight Python code, which if that had a speed ratio of 1. The Rust called by the Python code had a speed up of 17. There's some important caveats that we're going to address in the upcoming slides, that this test, this word counting test, which we'll elaborate on, was written in pure Python, and the interpreter is important of what we use to run the Python when comparing these. So we use CPython. Now, why did we use CPython? There's quite a few flavors of Python, and we'll just kind of review these to focus on why we use CPython. And if we sort the different flavors of Python by the package support and language features, one of the first that we have is Jython. And Jython's neat. It's a Java-based Python environment. It can run Python code in parallel. In the example I showed previously with the 17x speed up using CPython, it can't run Python code in parallel. So this can, but one of the limitations here is that the package support is still Python 2x. And next we have with more language features is IronPython, and that's a .NET-based Python environment. It can also run Python code in parallel, but it has limited package support, and it's while it's Python 3, it's still Python 3.4, so it doesn't have a lot of the newer language features that we've seen, and everything from 3.6 up. There's PyPy, and PyPy is cool because it's a Python just-in-time compiler written in what they call RPython, which is like a reduced Python instruction set. It can run Python code of 3.5. It can run it very fast because it's compiled, but the package interface is still slow. So one of Python's great strengths is reaching out to a large community of packages, and so with a slow interface, that can be problematic. Also, the JIT is slow at startup, and it can't run parallel Python code like the Jython and IronPython. We have Cython, which is compiled Python code. And that is fast compiled C code. It has parallel options, and it supports a lot of packages. Its disadvantages: it doesn't have the REPL. It doesn't have the ability to just type on the command line and iterate quickly to be able to do rapid development, which is one of Python's great strengths. Also, to really get these advantages with Cython, you have to use Cython's specific keywords. So that's why I focused on CPython, because CPython, it has a very large community and package support, and it includes the latest language features, so that you have that richness of the development environment to rely on community packages that may not have even been intended for Python. But its disadvantage is it's interpreted code, and it can't run in parallel. And those speed disadvantages are where the 17x speed up came in. And this is the reason, if we want to investigate this reason more, that 17x speed up, just to put a little more meat on the bones of those points. The reason for this is that Rust, so the reason for the speed up, where we have Rust, it's compiled like C, whereas we showed previously the CPython is interpreted. And Rust, also like C, can run in parallel while the CPython cannot. And the reason it can't is because of something known as the global interpreter lock, or the GIL. And the GIL, one can think of as having a work permit. So in CPython, you can have multiple threads running, but the threads run one at a time. So the thread, if you're running a thread and CPython wants to switch to another thread, there must be what's called a GIL switch. So it's basically like a different thread. If thread 1 needs to hand that work permit off to thread 2, and then there needs to be another GIL switch when thread 3 wants to run. There's been many attempts to remove the GIL, and they've been unsuccessful for the mainstream use for multiple reasons, of either not getting the intended performance increase or not being compatible with a lot of the user community packages. There is a very recent attempt that's going on that may prove fruitful, but until then, we're stuck with this GIL and having to run CPython in a single threaded use case. And I should say there is the option of running with multi-processes with CPython, but it's basically spinning up new processes of separate CPython programs and then having some sort of communication pipe between them. So if you want a finer grain parallel approach where you're actually sharing data, the same data in memory, such as you could do with multiple threads running in the same process, you have to look at languages like C or Rust. And CPython uses C to get its speedups. And so CPython, while the Python code that one's writing doesn't run in parallel, the underlying C code can. And that's because the underlying C code can bypass the GIL. And you see this when running numerically intensive software, such as when NumPy is running a say a matrix multiply, and it's using an underlying C library or Fortran library called BLAS, which is the basic linear algebra subroutines, and that code is highly optimized and it runs in parallel. And the reason why it can run in parallel is because it's written in C, and the Python has that GIL switch, which actually, while it prevents the Python code from running in parallel, the reason it's doing that is to allow the C code to run in parallel. So if Python already has a mechanism for running code in parallel with C, why look at Rust? And the reasons why to look at Rust is that the performance of Rust is similar to C, that there's a memory safety promise that we won't have data leaks, and there's concurrency management, that we're not going to have data races. So these promises of safety allow a programmer the freedom to be able to be more aggressive with the types of optimizations, especially with parallel optimizations, because you don't have to worry about those the data races or the memory leaks. To illustrate this, to illustrate using Pio3 and how it is able to do the interfacing in a clean manner between Python and Rust, we're going to show a couple demos. And so for the demo, I'm going to describe the problem. I'm going to show the Python code for this particular demo, and then actually for the demo, we'll be building the Rust code and running the code, and then also running it against the benchmark using PyTest. So the problem that we're looking at, which you said earlier for that 17x speedup, was the word count problems. More specifically, it's to count the number of times a specific word appears in a block of text. The block of text that we're interested in is the Zenith Python program, and the word that we're going to count is the word is. And so in the Zenith Python program, the word, or poem, the word is used 10 times. Now, there's not a lot of data here to process, so to make it a little more intensive, we're repeating this block of this poem block 1,000 times. So we would expect, since the block is repeated 1,000 times, the word is should be found 10,000 times. Now, if we look at how the interfacing is done, we're going to first look at how the Python code is written. And the Python code, for the straight Python code, without any parallel processing, it's a simple function, just search underscore py, and we pass in that poem that's been multiplied by 1,000 times, and then we're passing the word is, and we go through, split the poem up into individual lines, and then for each word in that line, we look to see if it's the word is and count it up, and then return the total, which should be 10,000. The PyTest framework that we're using is that we take this search function, and then we are going to pass it in for the benchmarking, and then we just assert that count that it returns is equal to 10,000. The Rust code to do the identical function is similar in length, and one of the reasons why is because of what Pio3 offers. And Pio3 offers attributes such as the Py function that allows you to define a Py function or a Python function in Rust. So it takes care of a lot of the boilerplate, and we have our Rust function now where that poem will be passed in, and then the word is will be passed in. And we're going to use the parallel processing library of Rayon, and it's going to split up the lines so that they can be sent out to multiple threads, and then each of those lines will be mapped to the function count line, and then all those functions will be run in parallel, and then their results will be aggregated up with the sum and then returned, and we should expect 10,000. So this count line that's going to be run for each line will take in the line, the string of text, split it, and then count the number of times the word is used. And so this is similar to what the Python code is doing. So we've shown both the Python code and the Rust code here. Well, how does the Rust code, we've seen the function, but how does it end up in the module? How in Rust do we represent a Python module? And Pyo3 simplifies that too by allowing you to define a module with another attribute, and we can define the word count module using these keywords, and then all you do is you just add the functions that you want in the module. So there's a couple more functions which I'm not going over but are in the Pyo3 examples library. But we take our function that we want to add, our search function right here, and then we just pass that to there along with the module information. And so that will then add the Python code to the module. Now, if we go back to the Python code, to the init.py, how do we use the Rust code? Well, we use it in a manner that's similar to how we would use the Python code, the functions there, that we simply include those. And we have here that Python function that we looked at. And then for the PyTest framework, we just say for the .search, and that simply calls the Rust code. So Pyo3 allows for a very straightforward way to interface the Rust code with the Python. Now, we need to do some additional work in Rust to be able to set up our project to use Pyo3. And we do that by modifying the cargo, and that should be actually .yaml, the cargo .yaml file. And in here, we just need to add that the Pyo3's dependency. And in this case, there's the ... because this example is in the Pyo3 directory. So it's simply saying the actual Pyo3 code is right above it. And we just say that we say that it's a library, and this will then build a shared library. And then it will also take care of linking the code appropriately so that it can be used in Python. And then now we'll look at a demo. Now that we've looked at the code, we want to run the code to see what performance results we get. The first thing we're going to do is create a directory. So we'll create the demo directory, and then we'll navigate into that directory. And next, we're going to clone the Pyo3 repository. Now that the repository is cloned, we'll navigate to the examples directory that we were looking at the code in. And I like to use pyenv to set my Python version, so I'll set it to 3.9.1. And I also, for an environment, like to use pip install, so we'll use that. And one of the files that's included in word count is the requirements file. And so this requirements development file, we'll just use pipenv to install the requirements for word count. Now that the requirements are installed, we're going to actually activate this shell, and we will run the setup program in Python to actually build the crate files and then link it with the Python code. Now that the code is compiled, we can test the code with PyTest. And so the tests are already there. So we run the tests and we can see what performance increase we get. So in this case, we see that the median performance increase when comparing our parallel version, which is benchmarked at a 1.0, with the Python-only sequential code, we see a 20 times speed increase, which is what we would expect to see with C code too. So now that we've seen the demo, let's look at how Rust code works with Python. So as we said, that CPython was designed to interface with C and C++ code. So Rust must use that same plumbing. And there's three methods that CPython can interface with the C code. One's called C types, the other is CFFI, and the final one's native. And so they go from simplicity, C types is the simplest to use, to the most complex, which is native, but here you're gaining more speed while C types tends to be slower. And if we look at some of the details here, for C types, this was designed for C. What's nice is you don't have to create a Python module to use it. You can also use this with standard DLL, so the DLL doesn't even have to be written for Python or Python aware of in any way. And it's a part of the standard library. You don't have to import any third-party libraries, but the devil's in the details, and you have to wrap everything, and it can be slow. CFFI is only for C. You don't have to learn the Python API, but it's not a standard in the Python library, and it has this ABI mode, which is similar to C types, but it also has an automated API mode to generate a Python module for you for faster access. So if you don't mind using a third-party library, CFFI could be a way to get a higher performance than C types without having to know the full native API. Pyo3 opted for the full native API, and that's because it's designed for C, and it's designed specifically for CPython, and so you have fast direct access to the CPython internals, but it does require learning a complex API, and it requires mapping C data types to Rust data types. But what's great is that Pyo3 takes care of that for you, so that's the real value add to gain the speed of this native interface, but then to help hide the complexity. And the way it does it is by acting as a buffer layer to that interface to be able to then have your Rust code. So we looked at previously a demo example of using Python with Rust, with the Pyo3 example from the Pyo3 library. And in this demo, we're going to actually make our own Python class, because the previous demo we were just writing Python functions with the modules, and here we're going to actually write a simple Python class in Rust and using Pyo3, and show how you would write it, compile it, and then run it in Python from the REPL. To do that, we need to make a Python class in Rust. And the way you start out is you can use cargo to simply create a class or a project. And so we're going to call this point, and we'll say it's a library because it'll be interfaced with Python's API. And so in this case, just have some information here, and then have the name and the crate type, which is again for the to be able to interface with the Python library. Now in this case, our previous demo, our code was sitting within the Pyo3 library source code, so we just referenced directly above the examples to where the code was. In this case, we're going to pull from crates.io, and we're going to pull the specific version of the Pyo3 library and then include that in our project. The actual Rust code to implement a Python class relies on Pyo3's attributes, so specifically the Py class, to define a Python class. Rust isn't object-oriented, so you define a structured data type instead. And then you can define the accessors, that these variables are going to be accessors for the Python class. And you can also define the methods within the Python class using the implementing the new function and saying that this new function will be the initialization routine for the Python class. Again, we add a Python module attribute, and then similar to what we did with adding functions, we instead just add a class. And this is a demo now, the building of the class and then running it in the REPL. For this demo, we're going to use the same directory as the first demo, but instead of using the clone Pyo3 repository, we're going to remove that, and we'll just use the pre-compiled version that we can get off crates.io. So to do that, we'll first remove the Pyo3 directory that we had downloaded previously, or cloned. And then next, what we're going to do is we're going to use cargo to create a library called point, and this will be the Rust code that will then be interfaced with Python. And we'll navigate to that point directory. Similar to the previous demo, we're going to use pyenv again, and then also pip env for setting up a virtual environment. This time we're going to install Maturin, which is a package from Pyo3. And this will allow us to do automated builds. We're going to build with this instead of using cargo. So we activate our shell. And we now need to make a couple modifications. Unlike the previous example where everything was already done for us, we'll need to modify Rust's configuration file called cargo, and we're going to need to add the library information so that it will be able to link with the libraries to interface with Python. And we're also going to include the dependencies of Pyo3. So we'll paste that in. And with this TOML file, we deleted the main dependencies header, and just using dependencies.pyo3 will allow us to specify for the Pyo3 dependency along with the version and what features are needed. So we'll save this cargo configuration file, and now we need to edit the Rust code. So when we created the project, cargo put a example file for us, and we're going to delete all of that. So we'll just delete the information here, and we'll copy in our new file. And our new file has a couple of headers. It's a similar style to what we saw before, but this time we're going to create a class in Python, and we do that by using a structure in Rust. Since Rust is more of a functional language, it doesn't have object-oriented features such as classes. So instead you create a struct, and then you put your data types, and to be able to put the methods that would go with the class, you use the implementation of for the struct point. So that will then create methods that can be used with it. So we'll use the new method, which will be a method equivalent to, in Python, of initializing the class. And then we just specify the PyModule attribute, and then specify some standard boilerplate for adding the class and returning a success value. And what we'll do is exit. And then to be able to compile the code, we don't use cargo. Instead, we use Turin, and we just say, and since we want to test it out first, we use the develop keyword, and this will just build the code and then place the compiled code into the Python extensions directory so that we can then access it. Once the code is built, we can now try it out in Python. So we'll load the Python interpreter, and we're going to import from our point package. So we'll say we're going to import point, or from the point package, import the point class. And then we can create the class, or an object of the class, using the standard Python notation. And we can then print the field values for x and y. You can see that those are the values that we assigned when we initialized the class. One of the questions is where exactly is this file? And to be able to look at that for the developer version, we can look at where the file location is. And actually this error is because I didn't import the point package itself, so I just pulled a class out of it. So if we import that, we can see that using the developer setting, it placed the package in with the other site packages for Python. Once we've tested our code and we're ready to create a release version that can be a package somebody could install, we can then create the wheel with using the build option. So we would simply type /, build, and this will create a wheel that could be either manually installed or it could be uploaded to PyPy. Now that the wheel is built, we can distribute it, and to do that we go to the target directory and then the subdirectory wheels. We can see here that the wheels have been built, and we can then distribute those. So the question is where to next. I'm wanting to look at more Pyo3 and whether to do a deep dive into Python and Pyo3, or to possibly try a workshop. And so comments are appreciated. And here are some of the references that were used. I'll also include those in the notes. And with that, we conclude this talk.